Welcome back to another episode of Crosstalk. I'm Olivia Lanes.
I'm Abby.
And today we are going to be interviewing Blake Johnson, who is our quantum capabilities architect at IBM Quantum. We have a great discussion ahead for you. We're going to be discussing what is performance software, like Qiskit, and what our strategy is going forward for not only benchmarking performance software, but also how Qiskit compares to other SDKs in the quantum ecosystem.
Let's dive into it. Blake, thank you so much for being here with us today in the YouTube studio. We are going to be talking all about Qiskit performance today. So just to dive straight into it, what do we mean when we say software performance or we talk about performance software?
Right, so software performance, in general terms, is about efficient use of space and time, right? So things that are either fast or that they use very little memory. For some kinds of software, right, like the solution quality there isn't like an answer. There's a range of answers. There's a sort of some sort of scale about sort of quality of answer. And so when you have that kind of scenario, then you're going to be maybe looking at trade-offs between space, time, and solution quality, which is certainly the case when we're talking about compiling or transpiling quantum circuits.
So if I was going to maybe anchor this in a real-world metaphor for those that aren't very knowledgeable about the software space, is this like when your laptop gets really hot and the fan starts whirring? Is that a performance issue? Normally the software is just taking too much time and resources to crunch the numbers it needs to crunch and do the things.
Sure, there are scenarios where your fan shouldn't be worrying because someone wrote some lousy software or something's gone wrong. There are some like heavy-duty computational tasks, right? Like when we use our laptops to do sort of major computations, which most of us are not doing on a day-to-day basis, the fans are going to whir.
And I guess in scientific computing and quantum computing specifically, you have to do a lot of these really sort of intensive computations, and performance becomes, I guess, very important in this space.
Yeah, for sure. Obviously, like our attention has been for a long time on the performance of the hardware. We need really high performance. We need really low error rates. We need lots of things out of our quantum hardware in order to get quantum computing into an era of eventual advantage, right, compared to classical computing. But there's a lot of work that you have to do in terms of being prepared to use that quantum computer in terms of representing your problem, compiling your circuits, post-processing the results, and all those things can involve expensive computations as well. And so like suddenly now, when we think about putting quantum computing together in terms of applications, workflows, and so on, suddenly now we actually have to care about the performance outside of the quantum machine itself.
Mm-hmm. So my question is, again, just talking about the software, what are the types of metrics that we need to keep track of? Which ones are the most important?
Sure. So like any piece of software, we're going to measure time, like how long it takes to do certain tasks. But particularly in the quantum space, for a piece of software that's preparing a workload to execute on a quantum system, quantum computer, we care about the quality of the circuit it prepares, right? Mm-hmm. Quantum circuits, particularly, quantum hardware is much more error prone than classical hardware. Errors are prevalent. We need to condense the size of circuits as much as possible in order to have the highest probability that the outcome will be faithful, will be useful to us, right? And so we're asking our quantum software to produce circuits that are small, right? That use the fewest number of qubits, use the fewest number of gates, that have the shortest depth, right? And so we're going to look for whenever we're measuring like the performance of our quantum software, we're going to look not just at how fast it runs, but sort of what are the qualities or characteristics of the circuit it produced, and does that give me the best chance for success when I move on to the execution phase with the quantum computer?
And a lot of that sort of reducing the depth of the circuit type of stuff and it's all sort of wrapped up in the transpilation step of your quantum computing workflow, right?
Right. So I think we think of different phases as you go through, right? We've seen this pattern emerge over and over again, looking at applications algorithm development, where you have to map a problem from a classical description to a quantum one. You're going to optimize that to execute, and then you finally go to execute on the quantum computer. And in those first phases, we have several different tasks that any SDK, quantum SDK, is going to participate in, right? So we're going to be looking at how efficiently can it construct and manipulate circuits, how efficiently can it construct and manipulate observables or operators representing the characteristics I'm going to measure the outcome of my circuit. And then there's going to be often synthesis tasks where I go from some sort of abstract mathematical description of a transformation to a concrete instantiation or actual sequence of operations that are going to implement it. And then finally I have to actually conform my circuit to the constraints of the hardware. So it has to only use the operations that it allows, has to use only the connectivity that's present. And so we have kind of these different phases of building, manipulating, synthesizing, and optimizing.
And all of those steps, the main way a user would sort of interact with that is through the Qiskit SDK, correct? And now that Qiskit went to version 1.0 earlier this year, and we know performance has been a major theme for just the last few releases of Qiskit. And why is it sort of the SDK in particular that has such a focus on performance right now? And what does it mean when we talk about a high performance quantum SDK?
Right, so I mean, I think we were transitioned in terms of the eras of quantum computing, right? Like there was an earlier era where we were using our quantum software maybe to learn about quantum mechanics, to learn about quantum computing, to kind of probe the properties of quantum computing systems. Mm-hmm. But our attention has turned because the systems have gotten more powerful, and suddenly people are now in sort of earnest search for finding different modes of utility and potentially eventually advantage with quantum systems. And so they want to sort of now they suddenly actually care about how does this whole workflow compare to the classical workflow that I'm maybe trying to displace or improve upon, right?
And I guess the Qiskit SDK of 3 years ago, when people were building 2-qubit Bell states, that SDK is not going to cut it, I guess, with the type of workflows that people are trying to execute today with hundreds of qubits.
Yeah, I mean, we may have even been kind of unaware of how it performed, right? Because if the only things we were building were sort of 2 to 5 qubit circuits, how well it performs and how long does it take to transpile a 100 qubit circuit?
We didn't have the queue times that we do.
It is maybe not as important, right? But so the SDK I mean, it exists within a broader set of tools now, but it is your touch point, your first touch point to sort of everything, right? So, and it's kind of involved in every one of those steps. So it has to be highly performant in order to sort of not become the bottleneck anywhere in that workflow.
Mm-hmm. What is the overall strategy that IBM is pursuing now and in the future to improve Qiskit performance?
Right, so Qiskit started out as a pure Python library, right? That was a choice that we made, but because Python was popular and accessible to our target audience, but also Python has this wonderful flavor that kind of everything can be kind of torn up and sort of you can change everything about a piece of Python code. So adaptability, flexibility was sort of one of the prize criteria in sort of the initial versions. Mm-hmm. But Python, for all of its benefits, is not a particularly fast programming language, right? It's not that the tool you pick up if you want to take speed and efficiency to the max. So we've started an effort actually 2 years ago now to replace the kind of internals of Qiskit with a high-performance Rust core.
Yes, I'm so excited about this. I find it... Okay, my coding nerd side is showing now, but I find it so...
I didn't know what Rust was until somebody mentioned it a year ago.
TLDR, Python, slow but easy to use. Rust, very fast but difficult to use.
No, I knew that.
Well, that's basically what you need to know.
Well, I think there are a lot of people who have been asking actually recently, am I going to need to know Rust in order to program with Qiskit in the future? But that's not the case, right?
That's the cool thing, and I'm sure Blake can say more on this, but the interface to Qiskit is still Python, but just under the hood, it's all Rust. So it's you get the best of both worlds. You get all the performance from the Rust side, but as an end user, you still get the nice, easy interface of Python.
Okay.
Correct me if I'm wrong.
This is exactly it, right? So we've started to oxidize Qiskit. So the internals are becoming sort of more and more this Rust library. And that project's not done, right? Like we started it 2 years ago. The aim is for it to be complete by the time we get to Qiskit SDK 2.0, which will be released about March of 2025. But sort of in the interim, sort of each SDK release has sort of another tranche of that work that is completed. And so, it started out with, Qiskit's kind of fundamental data structure for representing circuits when it manipulates them is something known as a directed acyclic graph. And Matthew Trainish, one of the first things in this project was to replace the graph library called NetworkX that Qiskit was using with a Rust re-implementation of the same. That's actually called RustWorks. It's a drop-in replacement. You can sort of use it. It kind of looks and feels like NetworkX, but it's much, much faster. All right, so that was the beginning of that journey. But sort of over time, sort of everything is being converted. And I would say we're a little over the halfway point now. But sort of with each sort of new piece that gets converted, you get sort of new performance benefits. And as Abby was just saying, one of the beautiful things about that is like we're doing this in the way that's like you have this high performance Rust core and then a Python interface to it. So your code can stay the same. It still looks and feels to you like a Python package, but what you're getting out of it is that higher performance library underneath.
And it sounds like there's more performance improvements to come if it's still in work in progress.
Yeah, for sure. I mean, like one of the things that's a bit challenging is you do this conversion, right? It's like you're trying to change the wheels on the car while it's driving. But like the team has been really successful in doing it. But you end up with these kind of awkward transition points where because some of the code is still Python, some of it's Rust, you can actually take some piece of code and make it a faster implementation in Rust, but because you're like calling it from Python more often, like you actually lose some of the benefit because of that sort of language barrier crossing. So there's actually some things that are kind of latent and waiting in Qiskit SDK 1.2, for instance, where like there's performance still to come, but we have to like now convert the Python caller as well. And so like most of that will be, most of the sort of user-facing parts of that will be present by the time we get to 1.3, but then by 2.0 you really have this kind of standalone Rust library. And that also lets us even contemplate maybe in the future like putting other shells around it. Like it doesn't just have to be Python, right? You could put a C++ shell or whatever, right? So you could think about other popular languages for different computational science communities and how they could also take advantage of the same high performance tool.
Great. Cool.
I'm excited. Everyone mark your calendars for Qiskit 2.0. Okay, so in all of this performance work that is going on, I'm assuming there's got to be some trade-offs, right? Can you maybe speak a bit to those?
Sure. I mean, like the most clear trade-off you always have when we're talking about optimizing circuits is sort of quality and speed. You can always try to find better circuits by trying harder, right? By doing searching more broadly. Maybe you have a randomized process and try more random trials. Like there's very clear ways that you can kind of trade speed and quality. Of course, as the user, we try to present that choice to you in Qiskit with a simple sort of optimization level flag so that you don't have to think deeply about sort of what pieces you're exposing. But then all that power is available if you know about the different passes and if you know that some particular expensive pass maybe is applicable and useful in your particular circuit.
So generally, if you want a better quality circuit, it's going to take you longer to transpile it, is what you're saying?
For sure. One of the cool benefits of this work of converting Qiskit's core to Rust is that the core has gotten so much faster that we've actually been sort of choosing to do more work with each optimization level because each sort of transpilation pass has gotten cheaper. Right, so like how much work we do at each optimization level is actually expanded because the transpilation passes are so much faster.
So you're saying if you're using like a Qiskit 1 point something stack and you're using optimization level 2, you're actually getting more than if you're using optimization level 2 from like a prior Qiskit version.
That's right.
That's cool.
In fact, a lot of what was reserved for optimization level 3, the highest optimization level in Qiskit, has been pulled into optimization level 2
Yeah.
because it's just so fast that there's like, why not?
So it's really important to update your Qiskit software.
Yeah, I was going to say, public service
Reminder to
announcement.
me.
Upgrade your Qiskit version now.
Cool. So speaking of comparing different versions of Qiskit, and in the future, of course, we'll probably want to be comparing different SDKs as well. How do we do that?
We need kind of common measures in order to understand like how different tools operate at the same task, right? And this is kind of the process of creating benchmarks. And there's been a lot of benchmarks in the quantum ecosystem. A lot of them have focused in the early days on benchmarks for quantum hardware, right?
Yeah.
We're talking about ways to measure error rates, crosstalk, things like quantum volume or speed with clops, right? There's also, you see things that are more application-oriented benchmarks, which are a little bit fraught with difficulty, at least in terms of communicating something useful, right? Because you see application benchmarks that are either like toy quantum problems, like Deutsch Joseph, Bernstein-Vazirani, which tell me something about complexity classes, but don't really tell me something about applications. Or you see things which sort of measure applications either at a too small of a scale or too large of a scale, right? Either too small because like there's no possibility of advantage at those scales, or too large because like if the runtime of my algorithm is hundreds or millions of years, like kind of who cares, right? Yeah. So our perspective is that one of the reasons that so many efforts to try to build application-oriented benchmarks have failed is that we haven't actually had a serious effort to kind of understand the performance of what the foundation is that they're sitting on, what from the software perspective, right? What are the ways that any algorithm or application, what are the tasks that they all have to do, and how do various software development kits perform at those kind of fundamental tasks?
Right, because I think in the past we've had problems basically where we felt like we were comparing apples to oranges, right? It's hard to make sure that all of the SDKs are doing the same thing for the same problem.
Exactly.
Yeah.
And everyone has their own metric that I guess they prefer over others. So then how do you compare like IBM stack to any other stack that's out there?
I don't know. Ask Blake.
Well, we have a new tool now. So we just released a new open source benchmarking suite called BenchPress. And it has tests that are designed to measure the performance of these kind of fundamental tasks that participate in sort of preparation for execution. And so it has tests for circuit construction, operator construction, circuit manipulation, synthesis, and optimization. And there's some tests that were created sort of brand new for this test suite, but then it also has, it kind of pulls in the best from what we saw out there. So I mean, there's a number of other test suites one in particular called Chasm Bench, another called Feynman, but one that is particularly new and that we thought was really interesting is actually a data set called HamLib. And it's a massive data set. There's over 1.5 million problems in HamLib that are problems in condensed matter physics, binary and discrete optimization, and chemistry. And it's pretty comprehensive in its coverage. And the beautiful thing about this data set is it describes those problems in sort of a natural language for quantum computing, because what they are, they're so-called Hamiltonians on qubits. So this is a problem representation that is kind of ideally suited for a quantum representation, and it's kind of like one step removed from a circuit, right? So you can take each one of these problems and try to synthesize a circuit that would be part of some sort of solution for measuring certain qualities of those Hamiltonians.
Cool.
I was wondering if we could go back to those 4 different metrics that you mentioned. You mentioned circuit construction, circuit manipulation, synthesis, and optimization.
Yeah.
Could we spend a minute just giving like a high-level summary of like what do those 4 things mean to like an individual user? Like circuit construction is when you build your circuit, right?
Yes.
And so we're talking about how fast that circuit is being built or how well it's being built. What do we mean with that metric?
For circuit construction, I mean, we're primarily talking about speed and memory usage, right?
Okay.
And it is pretty much as simple as that. I mean, there are other qualities you could measure, but they're starting to become a little bit more intangible, like how flexible is the circuit construction? how it can do abstract circuits as well as concrete circuits. And these intangibles are not things that like have specific benchmarks associated with them, but they're kind of characteristics. And actually, if you look at the kind of ecosystem of other software development kits, you notice that not every SDK even is the same at these kind of fundamentals of circuit construction. There are SDKs that sort of explicitly focus or exclusively focus on physical circuits once it's sort of already sort of constructed in the instruction set of the target system. And then there are others that sort of support different abstraction levels, where so you not have just concrete circuits, but you can also have sort of mathematical transformations. You have things in Qiskit like isometries, unitaries, Cliffords, right, as sort of abstract objects without an explicit representation of the gates yet at the time you build it.
Got it. And then circuit manipulation is somewhat similar. What is that?
So I mean, circuit manipulation can exist both in sort of the user construction phase as well as when you actually want to start to optimize the performance of execution when you're going to apply like error suppression or error mitigation to a circuit.
Oh,
right?
I
So
see.
like
Okay.
some circuit manipulations are of the form of like I want maybe I have some circuit and then I want to wish to find some unitary evolution and then I want a controlled version of that circuit that's already a manipulation, or I want to invert a circuit. You have a lot of algorithms that have sort of a mirror structure. You do some sort of something in forward direction, you have some sort of phase marking step, and you have some reverse evolution following it. And those are also circuit manipulations, right? Constructing like the forward and backwards version of a circuit.
And still sort of looking at speed of memory usage for that part of the...
Exactly.
Okay.
But then like you can also have things which take a circuit and then try to provide an error suppressed version of that same circuit by like dynamically decoupling it.
Right. You have to add gates and
Or I
stuff.
might want to twirl it in order to shape the noise to make it more suitable or amenable to an error mitigation method, right? And those are all manipulations of circuits.
And then synthesis was the next one.
Synthesis, right? And that's this part that goes from sort of an abstract mathematical definition to a concrete instantiation. And there, I mean, again, it's speed and memory, but their sort of algorithmic choices in how they do synthesis can lead to actually dramatic differences in speed.
You mean the algorithmic choices under the hood, like in the internals of Qiskit?
Yeah, like how do you, well, I mean, I guess speed and memory, and already at that point when we're talking about synthesis, we can start to talk about quality metrics associated with output, right? So let's take the case of like of a Clifford group operation, right? There's, when we're talking about small Clifford groups, like the Clifford group on 2 qubits, you can probably have a lookup table that tells you exactly the optimal circuit implementation in terms of fewest number of gates or shortest depth that implements that 2-qubit Clifford. But as soon as we're talking about like a 50-qubit Clifford or a 100-qubit Clifford, that task of how you synthesize that into an optimal circuit is already sort of already complex. And so there are algorithms that are guaranteed to produce a circuit which has the equivalent action, right? So it implements the desired operation, but the sort of the number of gates can vary wildly. And so actually new versions of Qiskit have better synthesis algorithms specifically for Clifford group operations. And in fact, they're optimal underneath a certain number of qubits.
So going back to the benchmarking thing again, I guess this is probably the question that I've been waiting to ask since we sat down. How does Qiskit perform relative to other SDKs?
Yeah, so this bench press tool, of course, is a test suite, but then we've also implemented the tests in a variety of different SDKs, both sort of commercial SDKs as well as some academic projects that we thought were interesting. So like we were talking about earlier, one of the first things that jumped out to us when implementing these tests in the various SDKs is that not all of them attempt to cover all 4 of these elements of building circuits, manipulating, synthesizing, and optimizing them, right? Almost every SDK is going to have some means to build a circuit, but those other three things may or may not be present. Like as we discussed, there are some tools that really only focus on building physical circuits, and so the idea of optimizing or synthesizing such circuits are not really present. One of the only tools that really is as complete as Qiskit in terms of having all these pieces you need to really sort of prepare for execution is Ticket. And Ticket is powerful and popular, but its performance compared to Qiskit, at least in some tasks, is worse, right? So on the 1,000+ tests that are in bench press, Qiskit is on average 29 times faster than Ticket and produces circuits with about half as many 2-qubit gates. So the performance of Qiskit really has come a long way, and is we're very proud that we kind of are in this leadership position now compared to the other tools that are out there.
And I think it's great that these this benchmarking suite is open source. So anyone out there that's building a Qiskit-like stack can hypothetically use this benchmarking suite to sort of see how their stack is performing compared to Qiskit, right?
Yeah, I mean, we'd love to see other tools get added to this benchmarking suite. And if you're one of the creators of one of those tools, we'd love to see you implement changes that use your tool in a better way, right? So because we really want to see what the best is from each one of these tools, and sort of. I love the competition, right? Because I mean, it's like we all benefit from it,
we can only push the field forward if we're all sort of being transparent and working together to push the technology forward, right?
Exactly, and I think having this kind of understanding of where we are, it can only benefit us. I mean, one of the things that sort of emerged, right, in the sort of comprehensive coverage or testing of Qiskit and these other SDKs is, you find ways in which you fail, in which your performance is worse, and it provides new opportunities to improve. And so that's exactly what we need.
Right. Can't be afraid of failure because it shows you what you need to do better. Okay, my last question is, what can developers and researchers do with the new high-performant Qiskit that they couldn't do a few years ago? Because I think that's really what's going to show how much progress we've made in this short amount of time.
Yeah. So I mean, obviously, like, people are working on larger scales, right? We're no longer talking about 2 to 10 qubit circuits. People are talking about circuits that are on scales which are not amenable to brute force simulation. And so, like, they're comparing to sort of best of breed computational methods from some other domain. But something which I think is interesting, particularly as we survey these different tools, is it's kind of become apparent that your tool may influence what kind of research questions you even ask, right? This HamLib data set we were talking about that has this sort of comprehensive coverage of problems in various domains of condensed matter physics, optimization, and chemistry, has problems in it that some SDKs, when you try to synthesize those problems, can take actually weeks or months for the synthesis
really?
task.
Just to like construct the circuits
Just
needed,
to construct
or?
the circuit.
And how long does it take in Qiskit?
Whereas, like, those same problems we see can be synthesized in less than an hour with Qiskit.
Okay.
So that's still an intense computational task, but the difference between an hour and a week could be the difference between you trying that problem or not, right? And so, like, it's really now kind of become apparent that the performance of our SDKs is actually something which can be opening or closing doors to the kinds of research problems we explore.
I think that is a great point to end on. So thank you so much for being here with us today, Blake. This has been a really, I've learned so much about performance and benchmarking from this conversation, and I'm going to go away right now and update my version of Qiskit.
Same.
Excellent.
Well, what a great talk that was with Blake. I personally never really knew before today how much the performance of your classical software can actually affect the performance of your whole quantum workflow.
Yeah. I was really interested in the conversation that we were having about Rust. I know he said that it was sort of like changing the wheels on a car while it's still running. But I was thinking in my head during the conversation, it's actually more like changing the engine while the car is still running.
Yeah. Well, that's it for this episode of Crosstalk. If you have any ideas for who we should interview next, leave it in the comments. Yeah, and we'll see you next time.
Yep. Don't forget to like and subscribe.